In 1665, Cambridge sat deserted. The plague had forced everyone to flee. Students, teachers, scholars, the entire academic community gone. Meanwhile, there was a young man, just 23 years old, sitting quietly in his mother's garden in Lincolnshire, gazing at the moon above. His name was Isaac Newton. He had no employment. He had no laboratory to conduct experiments. All he possessed was a notebook, a pen, an apple tree, and an abundance of idle hours. And he was about to confront a question so daring, so seemingly simple, that it would occupy and challenge his mind for the next 20 years. The question he pondered was this: why does the moon not fall down? Think about it when you look up at the night sky. The moon appears suspended, unmoving. It seems steady, permanent, as though it naturally belongs there, just as a painting belongs on a wall. Humans had been observing it for millennia, yet most treated it merely as part of the background. It was simply there, a fixture of the heavens. That was the conventional understanding. The sky held things in place. Aristotle had developed an entire philosophy around this idea. He claimed that earthly objects, rocks, water, fire, moved in straight lines. Rocks fell downward, fire rose upward. But the celestial bodies, the moon, planets, stars, were composed of a completely different substance, a fifth element. This element, known as the quintessence, had a natural motion that was not linear but circular. Therefore the moon traced its circular path because that was the inherent behavior of heavenly matter. It was a neat and satisfying explanation, and for nearly 2,000 years people accepted it without question. But Newton was not like most people. He had studied the work of Galileo, who had uncovered a critical truth about motion. Galileo had observed that when you release a rock, it falls every single time, regardless of size or composition. A cannonball and a musket ball, dropped from the same height, strike the ground simultaneously, remove the air, and every object near the earth still falls toward it. This is not a mere tendency or suggestion, it is a law, an unbreakable rule of nature. So Newton was sitting in that garden, staring at the moon, reflecting on Galileo's observations of falling objects, when a deeply unsettling thought began to take shape in his mind. If everything falls, then why does the moon remain suspended? Could the moon somehow be exempt from this universal rule? Was there an invisible platform holding it aloft? Or was there some entirely different phenomenon at work, something that had gone unnoticed by everyone until now? The popular story claims that an apple fell on his head. Almost certainly that is not what truly happened. Decades later, Newton's friend William Stoley recorded that Newton described the moment differently. He said he was simply pondering in the garden when the idea struck him that the force which caused an apple to fall from a tree might not be limited to just the vicinity of the ground. Perhaps this force reached much farther than previously imagined. Why not all the way to the moon? His gaze shifted from the apple to the moon and back again. And he asked himself a question no one had ever framed in quite that way before. What if the moon is actually falling? It sounds absurd, doesn't it? If the moon is indeed falling, why does it never collide with the earth? Why does it remain suspended night after night, century after century, continuously orbiting? If it is falling, it seems to be failing at the task. But pause for a moment. Let's examine carefully what falling really means. When I release a ball, it moves straight toward the center of the earth. It drops downward, gaining speed as it falls, and after a brief moment, it strikes the ground. That is the essence of falling. In this simple scenario, Galileo demonstrated that near the Earth's surface, every object in freefall accelerates at the same constant rate, approximately 32 feet per second for each passing second. In the first second, a dropped object falls roughly 16 feet. In the second second, it falls around 64 feet. The distance traveled increases proportionally to the square of the time, a relationship Galileo measured using inclined planes and timing devices like water clocks. These were elegant and precise experiments. But there is something important about falling. It does not require the object to be motionless at the start. What happens if the ball is moving sideways as well? What if, instead of merely dropping it, I throw it forward? Everyone has done this. You throw a ball, and it does not travel in a straight horizontal line, it curves. It moves forward while simultaneously falling. The harder you throw, the farther it travels before reaching the ground. The trajectory it follows forms a curve, called a parabola. Galileo understood this too. He explained that the ball's motion can be separated into two independent components occurring at the same time. Horizontally, the ball continues moving at the speed at which it was thrown. Gravity has no effect on this part. Vertically, the ball is still falling, accelerating downward exactly as if it had simply been dropped from that height. The two motions are independent, and when you combine them, you get this graceful, arching curve. So the ball is falling the whole time it is moving forward. It never stops falling. Gravity never takes a coffee break. The ball hits the ground not because it stops moving forward, but because the ground gets in the way. So, let me push this further. What if you could throw a ball ridiculously hard? I mean absurdly hard. What if you climbed to the top of a very tall mountain? A mountain so tall it pokes above the atmosphere, so there is no air resistance. And you had a cannon up there, and you fired a cannonball sideways horizontally as hard as you could with a small charge of powder. The ball flies forward, curves downward, and smashes into the ground a few miles away. Ordinary projectile. Motion. Nothing new. But now, you add more powder, more speed. The ball goes farther. Miles. 50 miles. 200 miles. The ball is still falling the whole time. Gravity never lets up. Every second the ball drops 16 feet closer to the ground. But the ball is also moving forward so quickly that a new factor becomes important. The Earth is round. When you toss a ball across a football field, the Earth's curvature is negligible. The ground appears flat enough. But if a cannonball travels hundreds of miles, the curvature of the Earth beneath it becomes significant. The surface literally drops away under the projectile. Over a single mile, the Earth's surface falls about 8 inches below a perfectly flat line. Over 10 miles it drops even more. The farther the ball travels, the more the ground curves away. Now, fire the cannonball fast enough, and something extraordinary happens. The ball continues falling toward the Earth as it always does, dropping 16 feet every second, but the Earth's surface curves away at the same rate. The ball falls 16 feet, and the ground below also drops 16 feet. The ball never approaches the surface. It just keeps moving forward. In effect, it falls in a circle. That is an orbit. This is Newton's famous cannonball thought experiment, the insight that unlocked the mystery. He even included a diagram in the Principia, a simple illustration of a mountain with cannonballs arcing from its peak, each one traveling farther until one circles the Earth completely. The moon is not floating in space. It is not resting on anything, nor is it carried on some invisible or crystalline sphere. The moon is falling continuously for billions of years. Its sideways motion is just fast enough that it keeps missing the Earth. Orbiting is, in essence, falling. A satellite traveling around the Earth is not resisting gravity, it is obeying it, tracing a continuous fall around the planet. It is entirely subject to gravity. It is falling every single moment. The only distinction between a satellite orbiting the Earth and a rock dropped from your hand is sideways velocity. One strikes the ground, the other continues to miss. Consider how remarkable this is. When you observe the space shuttle circling the Earth or the moon gliding across the night sky, it appears as if something is holding it up. It seems as though a force is counteracting gravity, pushing the moon outward, keeping it suspended. Yet no such force exists. Nothing is pushing the moon away from the Earth. Nothing is holding it aloft. It is simply falling. Its sideways motion ensures that it continues falling past the horizon, over and over, never landing. There is something even stranger that follows naturally from this concept. If you were inside that cannonball, falling along with it, you would experience weightlessness. You would float. Weightlessness is not the absence of gravity. It occurs when everything surrounding you is accelerating downward at the same rate. The cannonball is falling. You are falling. Your belongings, your food, everything inside is falling together. Nothing presses against anything else, so you drift freely, almost as if suspended in a gentle breeze. This is exactly what astronauts experience. They are not in zero gravity. The gravitational pull a few hundred miles above the Earth is nearly as strong as it is on the surface, perhaps only 10% weaker. They float because they are in free fall. The spacecraft and its occupants are falling around the Earth as a single system. Since everything is falling together, there is nothing to push against, nothing to create the sensation of weight. Weight, as it turns out, is not gravity itself. Weight is the force you feel when the floor or ground stops you from falling. Remove that support, and you would feel no weight at all, even though gravity continues to pull with full strength. This distinction between gravitational pull and the sensation of weight is one of the most elegant and profound insights in physics. It is all hidden within Newton's cannonball thought experiment. Once Newton had this concept clear in his mind, he could not let it go. The next question arose immediately obvious, yet brutally challenging. If the moon is falling toward the earth, acted upon by the same force that draws an apple from a tree, how strong is that force at the distance of the moon? Does it follow a specific rule? Can it be predicted? Here Newton made a bold leap. He formulated a reasoned hypothesis and designed a test. His guess was this: the force of gravity diminishes with distance from the center of the earth, and it does so in a precise way. Double the distance, and the force falls to 1/4 of its previous strength. Triple the distance, and the gravitational force drops to 1/9 of its original strength. In general, the force diminishes according to the square of the distance, what we now call the inverse square law, written as 1/r². But why did Newton propose this particular relationship? There were several reasons. First, it is a natural mathematical form. The intensity of light from a candle fades as the square of the distance. Sound behaves the same way. Any quantity that spreads evenly in all directions from a central source tends to follow this pattern, because the surface area of a sphere increases as the square of its radius. If gravity radiates outward in a similar manner, it would naturally obey the inverse square law. Another strong clue came from Kepler's third law of planetary motion, which relates a planet's orbital period to its distance from the sun. The law implies exactly this type of force. Mathematically, the cube of the orbital radius is proportional to the square of the orbital period. For a planet to maintain a circular orbit, the force pulling it inward must decrease as 1 over the square of the distance. This idea was not completely new. Several thinkers had hinted at it. Robert Hooke had discussed the possibility, and Christian Huygens had derived the formula for centripetal acceleration, the inward acceleration required to keep an object moving in a circle. The concept of an inverse square relationship was circulating in scientific circles, but no one had yet done the one thing that would definitively confirm it. No one had ever tested the inverse square law using actual numbers. Newton decided to do exactly that, and the test he devised was beautiful in its simplicity. It is now often called the moon test. Newton already knew the approximate distance from the Earth to the moon. The ancient Greeks had determined it long ago using clever observations of lunar eclipses. The moon lies about 60 Earth radii from the center of our planet. Not 60 miles, but 60 times the Earth's radius, 60 times farther than the distance from you to the center of the Earth. This value had been measured and confirmed by many astronomers over the centuries. Ptolemy estimated it at 59, Copernicus at 60, Huygens at 60, and Newton settled on 60, a figure accurate enough for his purposes. If gravity obeys the inverse square law, then the moon should experience a gravitational pull that is only 1 over 60 squared as strong as the pull we feel on Earth's surface. That works out to 1 over 3,600. In other words, the moon should accelerate toward the Earth 3,600 times more slowly than an apple does when it falls from a tree. There is a delightful coincidence here that simplifies the calculation. In our system of time, a second is 1/60th of a minute, and the Earth's radius is roughly 1/60th of the distance to the moon. These matching ratios make the arithmetic almost elegant enough to compute mentally. How fast does an apple accelerate? Galileo measured it precisely. Near the surface of the Earth, a falling object gains speed at 32 feet per second every second. In the first second of freefall, a dropped object falls about 16 feet. Applying the inverse square law, the moon should fall about 16 feet divided by 3,600 inches 1 second. That comes to roughly 1/120th of an inch, a vanishingly small distance. Yet Newton realized that this tiny deviation could be computed. Falling, for an orbiting body, simply means moving slightly away from a straight line. Using this principle, he could calculate exactly how far the moon drops in just 1 second of its orbital motion. If the moon were not being acted upon by gravity, it would simply continue in a straight line, moving tangentially to its orbit. Gravity, however, bends that straight path into a circular trajectory. The tiny deviation from a straight line during each second of motion is exactly how far the moon falls toward the Earth. We know the size of the moon's orbit because we know its distance from the planet. The circumference of its orbit is 2 times pi times the radius. We also know the time it takes the moon to complete one full orbit, roughly 27.3 days, or about 2,350,000 seconds. Using the circumference and the orbital period, you can calculate the moon's speed, and from the speed and the radius, determine the centripetal acceleration, the inward falling motion. Newton performed this calculation in 1666, at age 23, sitting in his mother's house in Woolsthorpe, Lincolnshire. He had no degree, no title, no funding, no laboratory, just a pen, paper, and a razor-sharp mind. He worked through the arithmetic, and the result came out slightly wrong. Not catastrophically wrong, not absurdly off, but wrong enough to be puzzling. The number he calculated for the moon's centripetal acceleration did not perfectly match the value predicted by applying the inverse square law to gravity at the Earth's surface. Depending on the historical account, the discrepancy was around 15 to 16%, maybe slightly more. It was close enough to be tantalizing, yet too far off to count as proof. A less meticulous thinker might have shrugged, noting that the agreement was pretty good. But Newton was not that kind of mind. He did not settle for almost or good enough. If the inverse square law were correct, the numbers had to match precisely, and they did not. So what had gone wrong? The problem was not the concept. The mathematics itself was sound. The error came from a single number Newton used in his calculation, the radius of the Earth. To translate the moon's orbit into real units miles, feet, you need to know the Earth's actual size. 60 Earth radii, fine, but how many miles is one radius? Newton used the best measurement available to English scholars at the time, about 60 English miles per degree of latitude. That number, standard in his era, was slightly too small. The modern value is closer to 69 miles per degree. Because Newton underestimated the Earth's size, everything derived from it, the moon's acceleration, the centripetal calculation, was off by roughly the same 15%. At first glance, the inverse square law seemed to fail. Newton, however, did not yet know the radius was incorrect. All he knew was that his elegant test had not produced a clean match. He also faced a deeper, purely mathematical challenge. His entire calculation assumed that the Earth's gravitational pull on the moon acted as though the entire planet's mass were concentrated at a single point at the center. But why should this be true? The Earth is not a point. It is a massive sphere roughly 8,000 miles across, with mass distributed throughout its interior. Some mass lies directly beneath the moon, some on the far side, some off at various angles. Each portion of the Earth exerts its own gravitational pull in slightly different directions and at slightly different distances. Intuition suggests that these myriad pulls combine into a single force pointing to the center, thanks to symmetry, but intuition is not proof. Actually summing the contributions of every piece of a spherical Earth at an external point is extremely challenging. You must integrate over the planet's volume, accounting for distance and direction of each infinitesimal element. Newton could not do it, not in 1666. The mathematical tools required, what we now call integral calculus, were still being developed. He had the beginnings, which he called the method of fluxions, but the sphere problem was one of the most difficult applications, and he could not yet solve it. So Newton faced two obstacles, the wrong Earth radius and the unproven theorem about the sphere's gravitational effect. Both blocked him from fully validating his theory of gravity. And here is something remarkable that tells you the kind of scientist he was. He put the entire problem aside. Not halfway, not tentatively, he shelved it completely. He did not publish, he did not boast, he did not claim to have almost solved it. He folded up his notes and moved on. For the next 18 years, Newton focused on other work, eventually returning to Cambridge. Newton became the Lucasian Professor of Mathematics at the remarkably young age of 26, holding one of the most prestigious academic positions in the world. During this period, he built the first functioning reflecting telescope, a revolutionary design that used a curved mirror instead of a lens, which significantly reduced optical distortions and worked beautifully. His work in optics was groundbreaking as well. He demonstrated that white light is actually a mixture of all colors by passing it through a prism, shattering centuries of misunderstanding about the nature of light. This discovery sparked a bitter and very public feud with Robert Hooke, who had competing theories about optics and the behavior of light. At the same time, Newton immersed himself deeply in alchemy, performing hundreds of experiments attempting to transmute metals and search for the legendary philosopher's stone. He meticulously documented his experiments, filling notebooks with coded symbols, chemical recipes, and observations. He also devoted enormous energy to theological studies, writing over 1,000,000 words analyzing the prophecies in the Book of Daniel and the Book of Revelation. During this time, he became increasingly secretive, paranoid, and difficult. And the moon problem, the question that had haunted him since his early years in Lincolnshire, remained untouched, quietly gathering dust in a drawer. Imagine what that must have felt like. At 24, Newton already grasped one of the most important scientific ideas in human history. Every instinct told him that the moon was falling toward the Earth under the same force that pulled an apple from a tree. Yet, the calculations did not perfectly align. The numbers were off by a small but critical fraction, and he could not yet prove that the mathematical setup was sound. So he put the notes aside, returned to Cambridge, and did not speak of them to anyone for nearly 2 decades. Many wonder why Newton did not simply share his discovery, publish it, or allow others to work out the missing pieces. But Newton's approach was entirely different. He was fiercely private about unfinished work, and having been burned once already in his dispute with Hooke over light, he refused to risk sharing ideas before they were flawless. Hooke had a notorious habit of claiming credit for discoveries, and Newton had no intention of giving him such an opportunity, especially with something as monumental as a theory of gravity. During these 18 years, Newton pursued other endeavors, some brilliant, some less so. The reflecting telescope advanced the field of astronomy, and his studies on optics revolutionized understanding of light. Yet, much of his other work, alchemy, hundreds of experiments in makeshift furnaces, and theological musings, appeared at least superficially to be dead ends. He experimented endlessly with metals, salts, and obscure compounds, searching for patterns and hidden truths while documenting coded alchemical formulas and philosophical interpretations. He wrote over 1,000,000 words on theological speculation regarding prophecy and apocalypse. It might seem frustrating from a modern perspective. Why not return to gravity when you are so close? But creativity is not mechanical. Newton needed time. He needed the mathematics to mature. He needed the correct value for the Earth's radius. And perhaps he even needed the distractions of alchemy and theology, which kept his mind active, curious, and flexible, so that when the missing pieces finally arrived, he was ready to assemble them. Meanwhile, across the English Channel, critical developments were taking place that Newton was unaware of. A French priest and astronomer, Jean Picard, was conducting the first highly precise measurements of the Earth's size. Picard was methodical, patient, and obsessive about accuracy, using instruments far superior to anything previously available. He mounted telescopic sights on his quadrants and sextants, a first in observational astronomy, and utilized Huygens's newly invented pendulum clocks for precise timing. Picard established a chain of 13 triangles stretching from Paris to Amiens along the Paris meridian, meticulously measuring angles to an astonishing precision of 10 seconds of arc. For comparison, Tycho Brahe, the greatest observer of the previous century, could only achieve an accuracy of 4 minutes of arc. Picard's measurements were therefore 24 times more precise, finally providing the reliable Earth radius data that Newton's calculations had desperately needed. Newton spent 2 years on this project, from 1669 to 1670. When he finished, he had a number. 1 degree of latitude along the Paris meridian measured about 69.5 miles, not the 60 miles the English scholars had long assumed. That difference, roughly 9.5 miles per degree, might seem small, but multiplied across 360 degrees, it added up to an Earth more than 3,000 miles larger in circumference than previously estimated. The correct radius was about 3,930 miles. Picard published this in 1,671 inches, a slim book called Mesures de la Terre, a masterpiece of precision that crossed the English Channel almost as an afterthought. The exact timing of Newton's discovery of Picard's measurement is debated. Some sources say he learned of it at a Royal Society meeting around 1682. Others suggest earlier. What is certain is what happened next. Newton plugged the corrected Earth radius into his old moon test calculation. Same logic, same setup, same inverse square assumption, but now with the correct radius, the numbers matched. This was one of the most important moments in science. Recalculating the moon's centripetal acceleration with the correct radius, Newton found the predicted value from the inverse square law matched observations to within 1–2%. The same gravitational force that makes an apple fall 16 feet in 1 second also makes the moon fall 1/120th of an inch per second, exactly as predicted. There is a story, possibly apocryphal, that Newton became so emotional at this realization he could not complete the arithmetic himself, needing someone else to check it because his hands were shaking. Whether true or not, the significance is clear. 20 years of knowing he was right, but unable to prove it, and a single measurement by a French astronomer made it all snap into focus. Yet Newton still faced a second challenge, the sphere theorem. He needed a rigorous proof that a uniform sphere attracts an external point as if all its mass were concentrated at the center. Without this, the theory rested on an assumption. This proof required a completely new kind of mathematics. Consider a sphere of uniform density and a point outside it. Each tiny mass element inside the sphere exerts a pull on the external point according to the inverse square law. Every element is at a different distance and direction, so Newton had to sum an infinite number of tiny forces. He solved this using a technique equivalent to modern shell integration. Imagine peeling the Earth like an onion. Each layer is a thin spherical shell. Newton proved that a thin uniform shell attracts an external point, as if all its mass were concentrated at the center. The geometry is elegant. For a point outside the shell, two small patches on opposite sides are considered, one closer but subtending a smaller area, the other farther but subtending a larger area. The larger area exactly compensates for the greater distance, and the two contributions balance perfectly. Summing all such pairs, the total pull points directly toward the center, with a magnitude as if all the mass were at a single point. The Earth is not one shell, but a solid sphere. Newton had to show that stacking shell upon shell from crust to iron core does not change the result. Each shell independently acts as a point mass at the center, so the entire collection behaves as one concentrated mass. Shell after shell, each pulling from the center, adding up to a single total pull. The proof is not only elegant but profoundly powerful, providing a firm mathematical foundation for the inverse square law of gravity. It took Newton until about 1684 or 1685 to fully resolve the remaining problems. By then, the moon test worked perfectly. The sphere theorem was proven, and the inverse square law of gravity stood on solid ground. Then, as if by fate, Edmund Halley entered the story. In January 1684, at a Royal Society meeting in London, three men, Edmund Halley, Robert Hooke, and Christopher Wren, were debating the planets. Halley was one of England's finest astronomers, already famous for cataloguing southern stars. Wren was the architect who had rebuilt London after the Great Fire, a man whose mind was as sharp in mathematics as in design. Hooke was brilliant, irascible, and convinced he had discovered everything first. The argument centered on a fundamental question. If the force pulling a planet toward the sun decreases as the inverse square of distance, what shape would the orbit take? Kepler had observed that planetary orbits are ellipses, not circles. Could this be derived mathematically from an inverse square law? Hooke claimed he had a proof but wanted to keep it secret, thinking others would try and fail. Nobody believed him. Wren offered a reward 40 shillings to anyone who could produce the proof within 2 months. When no one claimed it, Halley decided to visit Cambridge personally. In August 1684, he knocked on Newton's door and posed the question directly. If the sun's gravitational pull follows an inverse square law, what shape is the planet's orbit? Newton answered without hesitation. An ellipse. Halley, astonished, asked how he knew. Newton said he had calculated it years earlier. Halley requested to see the proof. Newton searched through his chaotic piles of papers but could not find it. He promised to redo the work. 3 months later, in November 1684, Halley received a 9-page manuscript titled De Motu Corporum in Gyrum, on the motion of bodies in orbit. Halley immediately recognized its significance. This was more than an answer about ellipses. It was the foundation of a completely new physics. Newton had not merely solved a single problem. He had sketched a framework capable of explaining the motion of every body in the solar system. Halley returned to Cambridge and urged Newton to expand the manuscript into a full book. Newton, despite being secretive and often stubborn, agreed. For the next 18 months he worked obsessively. He barely ate or slept. He would wander the Trinity College courtyard, stop midway, stand lost in thought for minutes, then return to his room without reaching the dining hall. His secretary noted that Newton rarely laughed during this period. The result, published in the summer of 1687, was Philosophia Naturalis Principia Mathematica, the Principia, a book that changed the world. Halley personally funded its publication, as the Royal Society had already exhausted its budget on an extravagant volume about the history of fish. The path to publication was not smooth. When the first book of the Principia reached the Royal Society, Robert Hooke claimed that Newton had stolen the idea of the inverse square law from him. Hooke demanded credit. Newton, who had clashed with Hooke before over optics, was furious. He went through his manuscript and deleted every reference to Hooke, nearly withdrawing the third book entirely. Without Halley's diplomacy, the Principia might have died in a fit of spite. Halley, both patient and persuasive, smoothed over the dispute and ensured the work survived, a reminder that science often depends on people who can navigate egos as much as equations. The Principia did more than solve the moon problem. It solved everything. Newton laid down 3 laws of motion and 1 law of universal gravitation, from which he derived an astonishing range of results. He explained why planets move in ellipses, the tides caused by the moon and sun, the equatorial bulge of the Earth, the precession of the equinoxes, and even how to calculate the mass of the sun from planetary orbits. He predicted comet paths and laid the foundations of celestial mechanics. At the heart of it all was one simple law: the force of gravity between 2 objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. That single rule governs everything from the fall of an apple to the orbit of the moon, from planetary motions to the shapes of galaxies. The moon problem, the question that began in a garden in Lincolnshire, was answered beautifully. The moon does fall. Every second, it drifts about 1/20 of an inch closer to Earth while simultaneously traveling sideways at roughly 2,200 miles per hour. Because the Earth is curved, as the moon falls a tiny fraction, the surface beneath it curves away by the same amount. The moon is constantly falling and endlessly missing its target, tracing a nearly circular path. This is not magic, nor some special celestial force. It is the same gravity that pulls your coffee toward the table and keeps the atmosphere bound to Earth. That force reaches the moon, the sun, and across the observable universe. It weakens with distance according to the inverse square law, but it never reaches zero. Newton's insight unified physics. Before him, terrestrial and celestial physics were considered separate. The corrupt, changeable world below the moon obeyed different rules than the eternal heavens above. Aristotle's division of realms suggested fundamentally different laws for earth and sky. Newton demolished that view. Rocks falling from cliffs and moons orbiting planets obey the same laws. The first great unification in physics, it showed the universe is one, operating under one set of principles. And yet the 20-year wait is crucial. Newton had the idea in 1666. He was right, but the proof, the mathematics, and the measurements all had to align. That patience, that quiet persistence, is what made this discovery timeless. The insight that the moon is falling was correct. The inverse square law was correct. The physics was right. And yet Newton put it away for 2 decades, not out of laziness or forgetfulness, but because the numbers were not precise enough and a critical theorem remained unproven. This is what real science looks like from the inside. It is not a flash of genius followed by champagne and applause. It is a flash of insight followed by years of grinding, doubting, checking, and waiting for the right measurements or the right mathematical tools to appear. Newton did not publish a half-finished theory. He did not shrug off a 15% discrepancy as probably just noise. He held himself to a standard of proof that was rigorous, almost punishing. And when the proof finally arrived, it came not from Newton alone, but from a French priest meticulously surveying the countryside. Picard never knew that his 2-year project measuring triangles across France would complete the greatest theory in natural philosophy. He was simply trying to make an accurate map. This is the lesson. Science is never a solo performance. Newton discovered gravity, but without Galileo's experiments on falling bodies, Kepler's painstaking planetary tables, Huygens' work on circular motion, and Picard's measurements of the Earth, the Principia would never have existed. As Newton himself said, If I have seen further, it is by standing on the shoulders of giants. Halley, the man who brought the Principia into existence, used Newton's laws to study comets. Reviewing historical records, he noticed a bright comet appearing in 1531, 1607, and 1682, roughly every 75 to 76 years. Using Newton's equations, Halley predicted its return in 1758, even though he would not live to see it. And in 1758, the comet appeared precisely where Newton's law said it would. It was named Halley's Comet, and every 75 years, it reminds us that a theory nurtured through decades of insight, frustration, and collaboration truly works. The universe really does obey the law. And the moon? Go outside tonight and look. That serene, pockmarked disk is anything but still. It hurtles through space at over 2,000 miles per hour, continuously falling toward Earth, yet never crashing, because its sideways speed exactly balances its fall. Gravity does not hold it up. Gravity pulls it down. What keeps it in orbit is motion sideways, pure and simple. Every orbit in the cosmos works the same way. The Earth around the Sun, Jupiter around its moons, the Sun around the center of the Milky Way, galaxies around each other. It is all falling, all missing, all obeying one universal law. And the word universal deserves emphasis. Before Newton, no one dared claim that a law discovered on one small planet applied everywhere. Newton's audacious leap that gravity governs the motions of everything, everywhere, was nothing short of revolutionary. Newton was essentially saying, I figured out how gravity works by watching things fall in England, and I am telling you, it works the same way on Jupiter. It works the same way on the moons of Saturn. It works the same way in distant star systems. The same rule, the same mathematics, the same inverse square law applies everywhere, always. That is what universal means. Not just common, not just widespread universal. No exceptions, no special cases. One law for the entire cosmos. Astonishingly, he was right. Every test, every observation, every spacecraft trajectory, every prediction about eclipses and comet returns confirms the same law. It remained unmodified for over 200 years until Einstein showed subtle adjustments were needed in extreme conditions, when gravity is intense or objects approach the speed of light. But for everything in ordinary experience, planets, moons, satellites, falling apples, Newton's law still works. It is still correct after more than 3 centuries. It took 20 years, a wrong number, an unproven theorem, a meticulous French priest, and a determined astronomer to turn a simple insight into the greatest scientific book ever written. That is how truth usually arrives, not with a thunderclap, but with a long wait and then a quiet click when the final piece falls into place. The next time you look at the moon, do not think of it as staying put. Think of it as falling perpetually, elegantly, and missing the Earth by just the right amount. Orbiting is simply falling sideways fast enough to keep missing. That understanding, once earned through patient observation and calculation, is yours now. Nobody can take it. Where in Newton's story did it click for you? Was it the cannonball on the mountain? The 20 years of patient silence? The realization that orbiting is just falling sideways? Whatever your moment is, hold on to it. It is yours, and it is extraordinary. And so, the story comes full circle. From a garden in Lincolnshire to the far reaches of the solar system, Newton's insight transformed our understanding of the universe. Gravity, once mysterious and separate for earth and sky, revealed itself as a single, elegant law governing everything from falling apples to orbiting moons, from comets to galaxies. It was never instant. It was never easy. It was 20 years of patience, perseverance, and collaboration. And that is the lesson. Truth is not a flash of genius. It is earned, piece by piece, sometimes waiting decades for the final number, the right theorem, the perfect observation. So the next time you look at the moon, remember, it is not suspended in the sky. It is falling, always falling. And in that fall it traces the invisible hand of a law discovered centuries ago, a law that is universal, unyielding, and utterly beautiful.